Hi, I'm Miss Hearn. Let's get started. In this video, we're going to learn about cliques in graph theory. In order to understand cliques, we need to remember a few definitions. For example, we need to remember what a complete graph is. A complete graph is a graph in which every pair of vertices is adjacent. In other words, each pair of vertices is connected with an edge. Here are two complete graphs, one with 3 vertices and one with 4 vertices. It's also helpful to remember how you can check for completeness when it's not so obvious. One way is to confirm that the degree of each vertex is 1 less than the number of vertices. For example, in this graph with 5 vertices, we would check that each vertex has degree 4. Remember, the degree of a vertex is the number of edges that meet at that vertex. So you can see vertex M has degree 4, and so do all of the other vertices on this graph. What that means is that each of the 5 vertices connects to the other 4 vertices. So we know we have a complete graph with 5 vertices. Now both complete and incomplete graphs can have subgraphs that are complete. Complete subgraphs are called cliques. Another definition we need to remember is the definition of a subgraph. A subgraph is a subset of the edges and vertices from a larger graph. For example, graph B is a subgraph of graph A because each of the vertices and edges in graph B is one of the vertices and edges in graph A. Now, both graphs that are complete and those that aren't may have subgraphs that are complete themselves. Complete subgraphs are called cliques. This is very similar to the sociology context of the word cliques, where a clique means a group of people who all know each other very well. So this would be a group of vertices within the graph that are each connected to the other. In this example, we're going to identify a clique of size 3 and list its vertices. A clique of size 3 would have 3 vertices, and each one of the vertices must be connected to the other. So we can see that the only 3 vertices that are each connected to the other are F, G, and H. There are no other 3 vertices that have this characteristic. In the next example, we're going to think about how we would know there are no cliques of size 4 or more in this graph. A clique of size 4 would have 4 vertices, each of them connected to the other 3. That means that each would have degree 3. So in order for a subgraph of this graph to be a clique of size 4, we would have to have 4 vertices of degree 3 or more. K has degree 2, L has degree 2, J has degree 2, I has degree 3, H has degree 3, F has degree 2, and G has degree 2. So we definitely don't have a situation where we could remove a subgraph from this graph and have 4 vertices of degree 3. The reason I say there are not enough vertices of degree 3 or greater is because when you remove a subgraph from the original graph, you reduce the degree of at least one of the vertices by detaching it from an edge. Now let's consider this example. Identify any clique of size 3, 4, or 5 in this graph by listing its vertices or indicate there are none. So remember, a clique of size 3 would have vertices of all degree 2. A clique of size 4 would have vertices of all degree 3, and a clique of size 5 would have vertices with all degree 4. So in order to have the possibility for a clique of degree 3, we need to have at least 3 vertices that are of degree 2 or greater. Let's check and see the degrees of the vertices in the graph we were given. So we have here 1 of degree 2, 1 of degree 4, 1 of degree 4, 1 of degree 3, and 1 of degree 3. So these are all 2 or greater. So we have a great likelihood of having multiple cliques of size 3. So whenever we're trying to count anything that's complicated and we're doing it by listing, we should do it in an orderly manner to avoid overcounting or undercounting. We want to make sure we count everything that's there, but we don't want to count anything twice. So I'm going to go in alphabetical order. The first letter in the alphabet in this graph is F. So I'm going to check for any cliques of size 3 that involve F, and I'll go straight to G next since G is after F in the alphabet. So F, G, and then G to H, and then H back to F. Yes, that would be a clique of size 3. And then I'm going to go back and still use FG and see if there's another possibility. So the only other vertex that G connects to is I. So we have F to G to I, and yes, it does connect back to F. So that would be another. All right, so we've tried the only possibilities with F to G. Let's try F to H, but not including G. So if I'm going from F to H, the other two vertices are I and J. So we could go H to I, because I comes before J in the alphabet, just to be organized, and see that yes, that does connect back to F. So F, H, and I would also be a clique of size 3. And then let's go ahead and take F to H again and see if we can use J. Yes, F, H, J would also be a clique of size 3. By the way, those are the only other possibilities for H. So now we're going to try with F and just I coming after H. If we used F and then I, and again, I don't want to go backwards in the alphabet and use G or H. So the only other letter left would be J. The problem here is that I doesn't actually connect to J. I and J are not adjacent to each other, so we cannot form a clique of size 3 using F and I. So we would just stop there. So these are all the cliques of size 3. All right, we're going to try a similar approach to finding cliques of size 4. However, we know that we're definitely not going to include the vertex J this time because it doesn't have degree 3 or greater. So we really only need to look at F, G, H, and I, which are the only 4 remaining vertices. We just need to check if they are a clique. Now, once we remove vertex J, then H is now down to degree 3 because it doesn't have this edge anymore. And F is now down to degree 3 as well. So now we have a graph with 4 vertices and all degree 3. So we can say that we have a clique F, G, H, I of size 4. Okay, and now what about size 5? Well, we don't have high enough degrees to have the possibility for a clique of size 5. Even if I went back to the original graph, which did have just enough vertices for a clique of size 5, you can see that the degrees are not great enough. For example, J is not connected to G and it's not connected to I. That's the reason why it doesn't have degree 4. It's because it's only connected to 2 of the other vertices, definitely not to all of them as we would see in a clique if we have a complete graph. So there are going to be none of this size. I hope you found this video helpful. If you did, please give it a thumbs up. That will help other students to find the video. You can also subscribe to my channel, Miss Hearn Mathematics, for more math videos.